One of the things that has made circuit analysis probably difficult and frustrating for you at this point is that every circuit you're confronted with has to be changed or reduced unless it's super, super simple. And we obviously have other ways of analyzing circuits that don't involve circuit reduction. In fact, a lot of circuits can't be reduced. So we need to come up with a way that when there are circuits that cannot be reduced, where resistors in series or parallel can't be combined, there aren't any, we need a more mathematical approach. And we have a way, we actually have two ways, of solving for all currents or all voltages, depending on what method you use. And this involves more math, less actual circuit changing. But it does mean that you need to check your work. This is one of those situations where you will always get an answer. It just might not be the right answer. So we will go through the process, both how to do this analysis technique and then also how to check and make sure your answers are valid. So the first thing we are going to talk about is nodal analysis. And in nodal analysis, we assign a voltage to every node that we don't know the voltage for, and then we apply Kirchhoff's current law. The best way to illustrate it is just to do it. We'll go through the process, and I'll just explain it as I go, and then, of course, you will get a chance to practice. So here is a circuit that has two sources and has nothing in series or in parallel. Well, the current sources and the resistors are in parallel, but that's really not going to do us any good. We cannot actually combine anything. So the process that we do in this case is, first of all, we identify where the nodes are, and there are three. Kind of makes the circuit look like a bullfrog, but anyway, then we actually assign a value to each one. So we have a reference node at the bottom, and in actuality, we don't need that one. We actually know the value of the voltage. So that one kind of goes away. And in general, that will be the case, that there will be one node that's the reference node, and we don't care about it because we already know the value is 0. So we assign values to the other two nodes. We have V1 and V2 in this case. And then what we do is we just put in some arbitrary current directions. Based on my understanding of how circuits work, I know that if the reference is 0 and there's another node in there, probably the current is going to flow from that node to ground. So usually I just put the direction of the current from the node towards ground to be towards ground. And between V1 and V2, I have no idea which voltage is larger. So I just arbitrarily assigned it to be left to right. And it doesn't matter if these aren't right. If we make a bad guess, that's fine. It won't make any difference. But what does need to happen is when current direction arrows are put in, they need to be used consistently. So the fact that there is an arrow going through a resistor means that we are assuming the voltage is dropping from the tail to the head of the arrow. So we are making the assumption that the voltage at the tail of the arrow is larger than the voltage at the head. If that's not true, that's fine. It will work out mathematically. But once we put arrows in, we need to be consistent. For instance, if we put the 10 ohm resistor arrow going from bottom to up, then if we wanted to figure out using Ohm's law what the current was, we'd have to use the 0, subtract V1, and then divide by 10 ohms. So it's easier if you're just always going towards the reference, then the 0 goes away. But it's up to you, whatever you want to do. The important thing is to be consistent. So the first thing we do is we're going to apply Kirchhoff's current law and Ohm's law simultaneously at the same time. And we're going to look at all the currents in and out of node V1 first. So we have 5 amps coming in, and remember we always treat currents going into the node as positive. And then we have the current through the 10 ohm going out, and we know that the value of that current is V1 over 10. That's what Ohm's law tells us. And then the value of the current through the 20 ohm resistor would be V1 minus V2 over 20. And those added together are going to have to equal 0. So that is an equation that just describes what's going into and out of the first node. Then we do the same thing for the second one. We do exactly the same process. This time we assume that the current coming through the 20 ohm resistor is positive because it's going into the node. So we treat it the same way, we just have a positive value instead of negative in front of it. So we have 2 amps coming in, which is positive. Then we add V1 minus V2 over 20, which gives us the current going through the 20 ohm resistor, and then we subtract V2 over 40, and when we combine all that, it also equals 0. So now we have a situation where we have 2 equations and 2 unknowns. So what we're going to do, we're going to get rid of the circuit. We don't really need it anymore. From here until we get a value for V1 and V2, we're just doing math. So we take each one of these equations, we have 2, and we simplify them. We simplify them in a way that is going to give us basically an equation with a coefficient in front of V1 and a coefficient in front of V2, and then whatever constants we have go on the right-hand side. So mathematically, we work this out, and the first equation is pretty easy. We basically move the V1 and V2s to the other side of the equation and flip them. And I do this basically because I don't like all the negative signs. Otherwise, if you don't do that, that's fine. Any way you simplify it is okay, as long as you simplify it correctly, and as long as the unknowns are on the left and the known values are on the right. Then other than that, you'll be fine. So the second equation, we do the same thing. We simplify that. And we now have 2 equations that we're actually going to use matrix algebra to solve. This is the easiest way to do it. Most calculators, even the cheap $20 Casios and TIs, can do this process. So generally, this is the way that I solve them. However, if you have a different way of doing this, if you like to use determinants, or you like to say you could multiply the bottom equation by 3 and add the 2 equations together and solve for V2 and then solve for V1. If you want to do that, that's fine. I'm just showing you this is the way I do it, and I always do it this way. And so, but if you come up with a different way, that's fine. So in using the matrix method, we take the coefficients here and we put them in a 4x4 matrix multiplied by our unknowns, and then on the right-hand side we have the 2 values that were known on this side. So we have the 5 and the 2, and they end up over there. And then all we do is we take this coefficient and move it to the other side, which means we invert it. And when we do that, we can solve this value. This is easy, like I said, to put in a calculator and solve. And we get 2 values of voltage. So we go back to our original circuit now that we've got these 2 values, and we go ahead and put them in. But how do we know those are right? We really don't have a good way of just looking at the circuit and telling that they're right. And I will tell you from experience that if you even get one sign wrong in your equations, you will definitely get answers, but they won't be correct. So the first part of this method is to use simultaneous equations and matrix algebra to solve for V1 and V2. The second part, and this is equally important, is to make sure the answers make sense, because you don't always know by looking at them whether they're right or not. They could be right, they could not be right. So what we do is we go through and we basically use Ohm's law, and we find the currents in the 10, the 20, and the 40, and we see if Kirchhoff's current law is upheld, because it should be. Remember that Ohm's law, Kirchhoff's current law, and Kirchhoff's voltage law have to be satisfied in every single electronic circuit. So if they're not, then there's a problem. So first of all, we can find the current in the 10 ohm resistor by just taking 54.29 volts. I did put the current directions in that we had before. And we find that there's 5.429 amps going through the 10 ohm resistor. Then, since we decided the current was going from left to right through the 20 ohm resistor, we're going to take V1 minus V2. Yes, I know V2 is bigger. It doesn't make any difference. Just stick with what you thought initially and it will all work out fine. So we take 54.29, we subtract 62.86 and divide by 20 ohms, and we get negative 0.429 amps. And all that means is that when we initially put that current direction in, we misguessed, and it's actually going the other way. It doesn't matter. Mathematically, it's correct. So don't go changing current directions now. Just keep it as it is and go with what you know. What we know is there's 5 amps coming into node 1, and there's the current through the 10 ohm resistor and the 20 ohm resistor going out. So if we add those two currents together, the current through the 10 ohm resistor and the current through the 20, we should get 5. So we take 5.429, we add negative 0.429, and we do get 5 amps, which is great. So we know that for that node, everything works, and pretty much you can usually assume if you've gotten one node that it works, but I usually like to go and look at the second one just to make sure, because I like to do math, which is silly, I know, but whatever. So we're going to look at the second node now, and we can get the current through the 40 ohm resistor by taking 62.86 and dividing by 40. We get 1.571 amps. Then again, we use the same current through the 20 ohm resistor. We already calculated that. And now, the way we've got it set up, the current through the 20 ohm resistor is coming into the node. The current through the 40 ohm resistor is going out. So what this means is that the 2 amps should be equal to the 40 ohm current minus the 20 ohm current. And if we go and take the 40 ohm current and subtract the 20 ohm current, we get 1.571 minus negative 0.429, and we do get 2 amps. So again, that works. It's incredibly important to take your answers and validate them. I'm going to talk more about that in a future lecture, but that's just as important as getting numbers, is to put the numbers back in the circuit and make sure they make sense. Because it's very easy to solve equations. It's not always easy to make sure that they're right. The other thing that we want to talk about is, what do you do when you're doing nodal analysis and you have a dependent source? We haven't done a lot of problems with dependent sources, but they do come up. So what do? We do the same thing, but we have to do a little bit more math to make the circuit solvable. So we do the same thing, but the first thing we do when we have a circuit with a dependent source is we find the relationship between the dependent source and the voltage or the current in the circuit that's driving it. So we actually have to kind of have a mathematical equation that relates that to what we're looking for. So again, it's best to look at an example. And we have here a circuit in which we have a current source and a dependent current source. So the dependent current source is down here. And it is depending on this current up here, which has been labeled. Remember that when you have a circuit with a dependent source, you have to have something there that tells you what current or voltage it's depending on. So if that's not marked, then the current really isn't going to, or the dependent source isn't really going to have much meaning. So we're going to go through and circle the nodes again. We have a big one at the top, and then we have a small one at the top of the dependent source. And then the reference node, and I'm going to actually leave this in here, is kind of this funky looking around the corner thing, because that's covering all wire. That's basically the only thing under there is wire. So I'm going to put that in, and I'm going to leave it in because it's easy to forget that the reference goes all the way around and meets at the 20 and 30 ohm resistors. So I'm actually, for the duration of the problem, going to leave the reference node in. Usually I drop it out, but this time I'm actually going to leave it there. So we label V1 and V2, and then we put in current directions just to make it easier for us to remember what we're doing. And then we find the relationship between this dependent source and the rest of the circuit. So we look at I1 and we find a value for I1 using Ohm's law. And Ohm's law says that I1 is just the current through the 20 ohm resistor, which would just be V1 divided by 20. So we set that out and kind of set it aside for a minute. So we said take that equation, and then we do exactly the same thing we've done before. So we look at the first node, V1, and V1 has 10 amps coming in. It has V1 minus V2 over 10 going out, and V1 over 20 going out. So we get a pretty straightforward equation for that part. And then actually, V2 node is also relatively straightforward. We have 5I1 coming in. We have V1 minus V2 over 10 going in, and then we have V2 over 30 going out. So we end up with this second equation, and the second equation has I1 in it. So that's why there's a little bit of a wrinkle when we're dealing with dependent sources. Now we're going to get rid of the circuit. Again, this part is all mathematical. And these are our three equations now. We basically have three equations and three unknowns. And the first thing we're going to do is simplify the circuit for node V1, because it's pretty much straightforward. It's exactly like what we've done before. So when we simplify that, we get 0.15 V1 minus 0.1 V2 equals 10. So that's great. Then what we're going to do, because we really don't care what I1 is, that's not the point of the problem. So we're going to take the value of I1 and we're going to substitute it into this equation down here. So basically we're going to go ahead and change that value, and now we have all V1s and V2s in the second equation, and we're going to go ahead and simplify that and put it back into its form that we have used before. And then the process is the same. Now that we've got two equations and two unknowns, we're going to take the coefficients and put them into an equation here, and then we're going to go on and solve it, and we get two values again down here. This is when we have to, again, go back to the original circuit and make sure these values make sense. The funny thing is, when I first did this problem, because I can design problems, but I don't know what the answer is either when I design them. I don't design them with an answer in mind. I just design them and then I solve them just like anyone else would. And the first two times I solved this circuit, I got distracted and left something out and got equally weird numbers, but they didn't work when I checked them. So I can't tell by looking at these whether they're valid or not, so I have to go back to the original circuit and find out. So we put the values in. V1 has a value of minus 88.89 volts. V2 has a value of minus 233.33 volts, and then I just left the reference node down here to remind us that it goes all the way up and around the corner. And then we just go and proceed to figure out values for currents. First of all, I1 is pretty easy to find. It's just V1 over 20. So we get a value of current for that as minus 4.44 amps. And we can figure out the current in the 10 ohm resistor by taking V1 minus V2 over 10. Remember, just be consistent with whatever current directions you put in. And when we go through and take V1 minus V2 over 10, we get 14.44 amps. If Kirchhoff's current law is going to work, these two currents should add up and give us 10. And they do. So that's a good sign. We know that the circuit works for node 1. And as I said, generally if it works for node 1, it's going to work for node 2, but I'm going to go ahead and look at node 2 anyway. And in this case, we're going to figure out what 5I1 is first. We take 5, we also already figured out what the value of I1 was, and we get minus 22.22 amps. So that is the current that is coming from this current source right into this node. And then we have already figured out this current here, because we figured it out for the last part, so we have minus 14.44 amps. And we're going to figure out the current in the 30 ohm resistor, which is just minus 233.33 volts divided by 30, and we get minus 7.78 amps. And in order for Kirchhoff's current law to be upheld, this current coming in plus this current going into this node has to equal this one going out. So minus 22.22 amps plus 14.44 does indeed give us minus 7.78. So again, we can be assured that this value is correct. So finding all the nodes at once is not so difficult, but assuring that those values are correct is just as important as the math you take to get there. This is a very powerful method of circuit analysis and makes oftentimes the analysis much, much easier than if you had to manipulate the circuit and change it. And this can be used on circuits that can be combined. You can use it on any circuit that we've done up to this point. It's just sometimes it's more trouble than it's worth when you can just reduce the circuit down. So next time we will talk about the other method of circuit analysis, and I'll see you then.